All right, good morning. Welcome, everyone. So, end of the first week, we are down to what? About 25, I would say. That's still a good number. I was expecting it to be less than 20. All right, let's get into our topic of chapter 1. And today we'll go over some of the common notations and some basics of circuit analysis that we will need for our for our studies. Okay. Okay, so I believe we stopped right here last class, analog versus digital. So we will encounter both analog signals versus digital signals also in our studies. Now, analog signals will have continuous values, meaning they have infinite possibilities, versus digital signals that have discrete levels. Okay. To go between the two modes, we use converters. So here is analog to digital converter. And if you want to convert a digital signal to analog, we use a DAC, digital to analog converters. And this is, of course, something that you'll study as you go along. Okay. So let's talk about notations. For current and for voltage, we use two subscript notations, right? Two subscript notations. So if we have a element which have two terminals, A and B, and we label the current for that element as IAB, we are taking a reference point at B. We simply state it's the current going from A to B. The first subscript is positive, second one is negative. Meaning if you were in the lab and you're trying to connect a multimeter into the circuit to measure this current, the positive lead for a multimeter would connect to point A, and the negative would connect to B. Conversely, if we state IBA, and if you're trying to measure the current IBA, it would simply mean the current flowing from point B to point A. So again, practical connection would be your positive terminal of the meter should go to point B, negative terminal should be connected to A. Mathematically, it makes no difference. Sorry, real life, it makes no difference. Mathematically, we insert a minus sign in there to actually balance out our equations. So IAB has the exact same magnitude as IBA. But depending on which reference direction we take for our analysis, we'll put a minus sign in front of it. We can also write IBA is equal to minus IAB. Okay, magnitude would be exactly the same. It all depends on what is our point of reference. So at the beginning of our analysis, and this is something you may have, I assume, would have learned in your past classes, is that when you begin an analysis, it doesn't matter what you choose. You make certain assumptions. Those assumptions are based on logic as well as certain laws of physics, right? If you have a source connected in there, current for a source always goes from minus to plus. This current goes from minus to plus. So then logic dictates that if you're going to have one source in a circuit and you have a resistor or an element connected directly to that source, then the current direction will follow the current coming from the source, right? You may assume any direction you want, even if it seems counterintuitive. But as long as you stick with those assumptions for the entire solution, your end answer, your final answer will always be correct. Okay. If you make an assumption and your final answer turns out to be negative, what does it mean? It only means that the current is flowing in the opposite direction. That's all it means. It doesn't mean anything else. So if you have an arrow that's pointing towards the right, you make an assumption for an arrow of the or direction of the current flowing towards the right. And let's say you end up with an answer that is -1 amp. All it means is the actual current is flowing in the left direction. So some other student might have chosen the left direction for their analysis. They would end up with an answer of 1 amp. And both of these answers are correct because they are signifying the exact same thing. Okay, so it doesn't matter what you choose. Make sense to everyone? Right? Then we also have two subscript notation for voltage. And for voltage, again, it means the same thing. When we say it's VAB, meaning positive reference of the meter, positive terminal of a meter is connected to point A, the negative end is connected to B. So VAB simply means you're measuring voltage at point A with reference to point B. That's all it is. Right? Voltage is nothing but the difference in electric potential between any 2 points. Those 2 points could be any 2 points in a circuit, could be across the exact same element, could be across like vastly different elements, doesn't really matter. Voltage is simply the difference in electric potential difference between any 2 points. And those 2 points can be anywhere in the circuit. It doesn't really matter. So VAB plus minus and VBA simply means my positive reference as B is at B and negative is at A. Okay, no difference. The magnitude or the values of both voltages will be exactly the same. They will not change. And so VAB is equal to minus VBA, or VBA is equal to minus VAB. And that's all it is. At this point, I always like to do like a two-dimensional chart, not a chart, but two-dimensional illustration of voltages could mean, right? So let's say this is zero level. And you have points A, B, C, and let's say D over here. And let's call this 0 as G or ground. Okay. Ground actually doesn't mean anything in this case. In our circuit, if you see a ground symbol, which is something like this, like 3 horizontal lines in the shape of a triangle, it notes the reference point in a circuit. Because if your circuit is running on a battery, like a DC battery cell, it's not physically connected to the earth. It's not physically connected to ground. Right? So let's say you have these 4 points in a circuit, A, B, C, D, and then G. So let's say 5 points. And let's take each line as 1 unit. So how far above G is C? What is the distance between G and C? 1 line, right? So let's say 1 volt. So if you say VC, meaning your reference is with ground, so it's VC is equal to VCG, then you don't need to use a 2 subscript notation. You simply state VC, the node voltage or the voltage at node C. If the second subscript is missing, then the reference point is implied. Meaning if there's a reference points in the circuit diagram with this kind of symbol, more often than not, we treat it as 0 volts. So with a single circuit notation like VA, VB, VC, VD, then it's just measured with 0. That's what it is. Okay, node voltages. So C is 1. How much is A? How much is B? And how much is D? I'll put down 2. Why? Because the two-dimensional image is telling me that D is already below my reference point. Again, the image is telling me or is showing me information. It's showing me that D is below 0. But if I was writing a mathematical equation, I would write down VD is minus 2 volts. That negative arrow mathematically is represented by that minus sign because my reference point is above. If your reference point is above that voltage level, above that node, it becomes minus. So now, what if my reference point was C? What is VAC? 3 volts. Absolutely. What about VAB? I heard negative 1 volt. Any other answers? I guess we all agree with that the difference, the magnitude is 1, right? The reference point. What is my reference point? Am I looking up or am I looking down? We're looking down. My reference point is above. VAB. Right? So my reference point is B. I am here, I'm at B, and I'm looking down at A. Does that make sense? And so it's minus 1 volt. Oh, minus 1 volt. Okay, so again, voltage levels, I especially like to do this because in circuits, you will often, as an electrical engineer, you often need to think very, very quickly, depending on where your reference point is. Okay, and everybody has their own methods. I'm not here to change those methods. If you are already comfortable with a specific method in determining the voltage levels in a circuit and current in a circuit, then you stick with what works for you. Okay, this is just an additional illustration. And if you find it easier to use this, feel free to run with this. If you already have something that works for you, stick with that. Okay, let's take a pause. Let me know if you have any questions. If you're online, then please do not type it in the chat window, right? If you have a question, just speak up. There's a speaker in the classroom. And so I and everyone else here in the room would be able to hear it. Yes. So VAB. So VAB would be, if I was measuring VAB, the positive reference of the meter would be at at A, negative would be at B. So negative reference would be at B, and so it's a higher level. It's higher than A, and so negative. Okay. All right, let's go to the next. So the notations we'll use for this specific course, you can break it down for DC as well as for AC. So nonlinear devices right now, we'll work with diodes, we'll work with transistors, right? And in both cases, there will be circuits where you would apply an AC voltage and a DC, an AC signal and a DC signal at the same time. In fact, one of the most common and the biggest application of a transistor is to use it as an amplifier. Right? An amplifier. You have used op amps. In 113, you learned about op amps, right? But there you were learning about op amps as an off-the-shelf component. You took an op amp and you added some more components in there and you used it to create something. And that is the beauty of an op amp, operational amplifier. But that op amp is created using hundreds of transistors. Well, if not hundreds, at least tens of transistors. So you take those transistors, you create a circuit out of it, you put it on one single chip, and you get an operational amplifier. And then you add a few more components in there, and you can create anything you want within the circuit design. Okay. So an op amp, if you use it for amplification, let's say the gain of an op amp is 100. Ideal op amp, the gain is infinite. But typical op amps, you can design a circuit with gain in tens, in hundreds, and even in thousands. So let's say you have an op amp with a gain of 100. If you apply 1 volt to it, what would be the output? 100 volts. So why not just take like 2 or 3 volts, apply it to an op amp, and obtain like 200 or 300 volts? Exactly. Energy does not come from from thin air. Obviously, we have the law of conservation of energy. Energy is never transformed, created. It's always never destroyed or created, but it transforms. Right? Electrical energy can be transformed into visible rays. That's how we get LEDs. More often than not, it's always accompanied by thermal energy, dissipated as heat. Okay, so it's always transformed. So if you have an op amp and you apply a DC source of like 10 volts to it, and you apply an AC signal, your output cannot exceed the DC source. And what that op amp is doing is it's simply taking the AC, mixing it with the DC. In a way, you're giving the shape of the AC waveform to the DC. Okay, so the power comes from the DC. It does not come from thin air. So you cannot use it just for power generation. And so oftentimes we will look at circuits where you have both AC and DC signals, and you need to distinguish between the two. So if you use uppercase letters or capital letters with capital or uppercase subscripts, we refer to DC voltages. So DC is all uppercase or capital letters. And AC is noted with lowercase or small letters. Okay. And so you see that here. The total signal is noted by the subscript of T. So the quantity, voltage or current, is illustrated or noted with lowercase, and then the subscript is uppercase. And that signifies there is a DC component as well as an AC component to that quantity. Okay, so VT indicates we are talking about voltage, and that voltage has a DC quantity or DC level, plus it has an AC level also. So oftentimes you will see signals represented. Let's say, for instance, if you take a transistor, the transistor would have a voltage measured between base and emitter, VBE. And so if you see a notation like this, VBE, that is my lowercase letter, that signifies it has the DC voltage measured at B and E, plus the AC input signal measured at those same terminals. Okay. And let's take a pause. Let me know if you have any questions. So far, so good. Okay. All right, sources. You may have studied this, right? 113 again at the beginning. If you have a circle notation or anything, it could signify a source or it could signify a meter. Meters are not used. I mean, the meter notations are not used as much, but if you have an arrow through it that goes as an angle, it's usually a meter. You won't see those anymore nowadays. And then if you have a circle, the plus and a minus sign, it signifies a voltage source. And here it signifies the arrow is the direction the current is. Actually, that's not right on source. This is simply pointing at the polarity of the voltage source. Okay. The circle means the source is independent. Okay. Meaning it can supply its rated quantity irrespective of what the load is doing. The load in this case is basically anything that is connected to the source. So it doesn't matter if the load is 1 ohm or 10 ohms or 100 ohms or 1,000 ohms. If a source is rated to supply 10 volts, it will keep supplying 10 volts, ideal source. Okay. If a current source is rated for 1 amp, doesn't matter what is connected to its terminals, whether it's 1,000 ohms or whether it's 1 ohm, that source will supply 1 amp. It will vary the output voltage, but it will keep the current constant. Okay. So have you ever used a current source? I'm assuming everybody's used a voltage source. How about current sources? Where have you used a current source? Everybody has used it because it's not a separate box. If you go to the lab and you see a power supply, that is a voltage source and it is a current source. There is absolutely no difference. The only difference is in the mode of operation. If you run that power supply unit, the PSU, power supply unit, in constant voltage mode, CV mode, then it's a voltage source. But at the same time, that voltage source is supplying current. You cannot have voltage without current. You cannot have current without voltage. But it keeps the voltage constant. It would vary the current. If it's a 1 volt source and a 1 ohm resistor, current is 1 amp. If it's a 1 volt source and a 10 ohm resistor, current is V equals IR. I is V over R, 1 over 10. So 1/10, 0.1. Right? So the higher the resistance, the lower the current. So it'll keep 1 volt constant, but before with 1 ohm resistor, the current was 1 amp. Now it's 0.1 amp. If you go to 0.1 ohm, the current would be 10 amps. So it will change the current, but keep the voltage constant. Hence, we refer to the source as running in constant voltage mode or as acting as a voltage source. If you run in constant current mode, CC mode, then it will keep the current constant and it will change the voltage. So if you set the power supply to supply 1 amp, and let's say you have 1 ohm connected to its terminals, then your output voltage is now 1 volt. If you change the load resistor to 10 ohms, what would you get? Supplying 1 amp, but now 10 ohms, 10 volts, right? So it changed the voltage, but it kept the current constant. Hence, the same power supply unit is now running or functioning as a current source. That's all it means. It's independent. It does not depend on anything else to supply its rated quantity. Hence the circle. The diamond, so these are independent sources. Which is basically above. And these are dependent sources. Dependent sources are noted with a diamond, both the dependent voltage source and dependent current source, but they depend on some other quantity in some other part of the circuit to supply its rated voltage or current. And we use these often in our models, especially for transistors. We'll use it as a dependent current source or a dependent voltage source. So you could say it's a dependent voltage source that supplies 3 volts, but it depends on something else in some other part of the circuit. It'd be like a multiplication factor or a division factor or something. One of the most common examples I like to use is as a voltage divider network. If you apply a voltage to a series connection of resistors, let's say you supply 10 volts between the outer terminals, right? Let's actually make it, let's make it 3 volts. 3 volts applied from the top to the bottom series connection of resistors. And all 3 resistors are equal. Let's see, R ohms, R ohms, R ohms. What is the value of the voltage across each one of the resistors? 1 volt, right? So you'd get plus minus 1, plus minus 1, plus minus 1. What is the output from this point to this point? 2 volts. So I can say, if I connect something right here across these 2 bottom resistors, that voltage is dependent on the supply voltage coming from the top. And the equation to do that, let's say it's V out. Let's call this V in. And let's call this V out. VO is 2/3 times V in. If V in changes and goes to 6 volts, I'm just speaking easy numbers, I can still predict what the output voltage is going to be. 2/3 of 6, right? 2 volts. I mean 4 volts. So V out is dependent on some other part of the circuit, and it's a dependent source. This is just a practical example, but when we get to numerical models, as I said, for some of our models, especially transistors, we will actually use a model because the output of the transistor is dependent on some other part of the circuit. So 3-terminal device. So there are multiple factors that that go into that model. And so it depends on some other part of the circuit. So for theoretical analysis, these dependent sources are very, very useful. All right, how should you approach? Your approach for problem solving would be to first read and identify the problem statement. Okay, establish the problem statement. What is it that we're trying to do? Then extract as much information as we can from the entire question. And sometimes everything is not stated in words. Actually, not sometimes, oftentimes. It's not stated in words. Information will be in the circuit diagram. Information will be in a graph or a chart. For instance, you might come across a graph or a chart that looks like this. Okay. You'll have time on the x-axis. Here it might be the voltage or current or power or energy, any other physical quantity. Nothing will be given to you in the problem statement. They might just, okay, here's a circuit diagram, find V out. Okay. So it would be your responsibility as an engineer to look at everything. The T would be in seconds or milliseconds or microseconds or even nanoseconds. If you miss the unit prefix, if there's a milli in there and you did not take that into account, your entire solution is off by a factor of 1,000. Okay, so you would do everything correctly, but your answer would be incorrect. Now, when you're taking my class, I'm lenient. So if you make a mistake like that, if you make an error like that, I might deduct like maybe 1 point. Okay, not much. Maybe 2 points, depending on what the circuit is. But if you're an engineer, you're designing a system, so you're working on an ECU module for a car, and you make an error like this, it's probably going to get you fired. So while you are in college and you make this mistake, it's okay. It's forgivable. You learn, right? But then you need to train yourself to look for these tiny details. Okay, so extract as much information as you can from the circuit diagram, from the graphs and the charts, from the words, from the problem statement. So basically, given information. Define your unknowns. What is it that you're trying to find, right? What is it that you're trying to determine? There's voltage, current, power, resistance. You would make lots of assumptions in there, okay? And that is fine. You can make assumptions, but those assumptions are based on logic. They're based on certain rules, right? And once you're done with your solution, you go back and you see if your end results match up with your assumptions. And so you make your assumptions, but those assumptions are based on rules, laws, and certain logic. If you have a source, as I said, if you have a source in a circuit with a plus and a minus sign, current logic dictates, laws of physics dictate that the current is going to flow from minus to plus. You can, of course, choose the opposite direction and still do your analysis, but wouldn't make any logical sense. If you outline your approach, then you analyze using any method you want. So there'll be multiple methods, multiple approaches. Then you verify your results, compare with your assumptions at the beginning. Do they make sense or not, right? If at the beginning of your analysis, you make an assumption that whatever assumption you make, voltage is between 8 or 10 volts, and you obtain an answer of like 7.5. So, well, maybe that doesn't make sense. So let me go ahead and change my assumption. Let's see what I get. And so you go through an iterative approach. You make an assumption, go back to the beginning, check and verify whether your answers make sense or not. Otherwise, you change your assumptions and you begin again. And then, of course, backed up by simulations and calculations.
Professor?
Yeah.
I have a question.
Yeah, go ahead.
Just now you said the current flow from negative to positive?
Or a source. Or a source. So if you're a source, the current goes from minus to plus. And then you connect a resistor to it. Current goes through here, causes a voltage drop plus to minus. So for all other passive components, which are absorbing energy, it always goes from plus to minus. Except for a source. A source is supplying energy, so it always goes from minus to plus. Okay. Otherwise, our equations would never work. Law of conservation of energy would never be satisfied. Just to take that example a bit further, we all have used our devices, mobile devices to charge, right? Laptop adapters, mobile chargers, tablet chargers, and so on and so forth. If I asked you for the power rating of your laptop adapter, let's say it's 50 watts, what would you say? You would say my adapter is 50 watts. But if I was to mathematically write an equation for that power, it would actually be minus 50 watts. Again, it's only for mathematical purposes. My power supply, my adapter is supplying 50 watts. So mathematically, if I want to write an equation, I would say the power is minus 50 watts. But we never say that in real life. In real life, all we say it's supplying. It supplies 500 watts or supplies 50 watts, not minus 50. The minus is for us humans to balance out our equations.
Thank you, Professor. One more question. In homework 2 in the Connect, there's a question asking you to find the Thevenin resistance of the circuit. And in the circuit, there's dependent current source, but
Yeah, it's
the
coming up.
problem.
It's in the next few slides.
Okay, sorry.
So that should take care of it. So let's see, it's 11:46. If I don't get through all the slides, I will go beyond the time. If you need to leave, feel free to leave at 11. Okay, but I'll keep on going for a few more minutes and I will record everything. Okay. All right, so reasonable numbers. Reasonable numbers mean that if you are making a calculation, let's say, for example, your power supply is 10 volts in the circuit, and you go through your calculation and you end up with a number that is 15 volts. That's not reasonable, right? Again, energy cannot come from thin air. So if a circuit has 10 volts, the max value you should obtain in there should be 10 volts. Cannot be more than that. Okay, so if a number seems unreasonable like that, you need to keep a lookout for that. Otherwise, there's an error in your calculation somewhere. Okay, there's AC signal limits, the same thing. Circuit current range, the same thing. If a source or a supply is supplying only like 1 amp, like say 10 amps or 10 milliamps for that matter, whatever the number is, your answers cannot exceed that limit. Okay, there's very few instances where that can happen. Oscillator, where you have energy exchange taking place between a capacitor and an inductor, like a second order circuit or a higher order circuit, it is possible to obtain voltages that are larger than the supplied voltage. But again, we are not talking about any of those in this class. Okay. Calculated component values, all of those, again, keep a lookout for what seems reasonable. Okay. And as we go along with some examples, it'll start making more sense. Right. Circuit analysis, as I said, you only need these 3 equations. Node voltage analysis or nodal analysis is basically Ohm's law plus KCL, and mesh current analysis is Ohm's law plus KVL. Okay, and that is of course the power equation. Electrical power is the product of voltage and current. P is equal to VI or P is equal to IV. And from Ohm's law, V equals IR, we can also create 2 more equations. Power P is equal to I square times R or V square over R. Again, these 3 principles, these 3 equations are all we need to solve for any electrical circuit. Okay. So if you haven't taken a look at those in a while, this is the time to brush up. So the homework and the quiz for the weekend is all, again, as I posted in the announcement yesterday, it's based on, you'll need Ohm's law a little bit, current division, voltage division, and then Thevenin Norton. Okay. All right, voltage division. If you apply a voltage to a series connection of resistors, the voltage gets divided in proportion to the value of the resistors. It's derived again from Ohm's law. Voltage division principle is simply a shortcut. It allows you to skip like a couple of steps. That's all. So if I was to find the current flowing through here, what I would do is I would find Req, and Req, because it's series connection, would be the sum of the 4 resistors, right? In this case, it would be 10 kilo ohms, and I would find I as 15 divided by 10,000 and 1.5 milliamps. And then from I can find the voltage drop across each resistor, right? So I can write VR1. In this case, we are using two subscripts, but VR1 is simply referring to the voltage across element R1. Okay, so it's not actually two subscripts in that sense. So VR1 would simply be I times R1. And we can write it's 1.5 milliamps times 1 kilo ohm, be 1.5 volts. Voltage division principle simply states when you apply a voltage across a series connection of resistors, a fraction of that supply voltage appears across each resistor, and the fraction is directly proportional to the ratio of the resistor to Req. And so VR1 is simply V total times R1 over Req. That's it. That's the voltage division principle. Okay. And then current division is the same, but there is parallel connection of currents. And so I can write I1, and I'm going to move along here. I1 is a fraction of Is, which is the supply current. The fraction is given by the ratio of Req to R1, flipped. One other thing to keep in mind is when you determine Req for parallel resistors, that Req is always smaller than the smallest resistor in that network. Meaning Req for this will always be less than 10. If you get Req more than 10, then there's an error somewhere in your calculation. Okay. Yeah, I'm not going to get through these slides in time. So that's current division. Then Thevenin and Norton. Okay. How many of you remember Thevenin and Norton? Okay, that's good. It's good. You have access to your 113 notes. Hopefully. This is a very important concept. As an electrical engineer, you would use this again and again and again throughout your career. Okay. Now, having said that, we are not going to analyze very complicated circuits, but you would use Thevenin and Norton to quickly analyze some portion of a circuit and find the Thevenin resistance and the Thevenin voltage being applied. Simple reason is this. If you have a voltage source like this, Vs, and let's say you're applying it to a resistor R1. So what is the voltage across R1? Vs, we already know that, right? What if we place another resistor here? Now it's different. Now we don't know what it is. We need to find the voltage at the midpoint as seen by R1. So Thevenin and Norton theorems, they were postulated in the late 1800s by a French telegraph engineer known as Leon Charles Thevenin. And what he postulated was if you take a linear circuit, a large linear circuit comprised of sources, dependent sources with linear components, you could describe everything in that circuit with one single voltage source. Doesn't matter how many sources it had, but you could describe everything with one single voltage source in series with one single resistance. That's it. That's Thevenin theorem. So you have this large circuit right here, and you want to find out the voltage across R6. Then you remove R6 from your analysis and analyze the rest of the circuit from those 2 points, And I would say those 2 points are the terminals of analysis. Okay, So you want to find the Thevenin circuit as seen by R6, and makes a big difference. Let's say there's 25 students in the class, okay? If somebody's standing outside and is asked, how many people do you see in the classroom? They would say 25 plus 1, 26. If somebody asks me, how many people do I see in the classroom? I have to remove myself from that count. And I say, I only see 25, okay? So if the question being asked is, determine the Thevenin equivalent circuit as seen by a particular component, you remove that component from your analysis and analyze the rest of the circuit. And then you can represent the rest of the circuit as VTH and RTH, and your R6 is connected right here. Does that make sense to everyone? And that is the purpose of Thevenin Norton. You want to find the voltage or the current between two particular terminals of analysis. So if I mark these terminals as A and B, I would say A and B are my terminals of analysis. And this is also what I'll be asking of you on Monday. Okay. I'm not going to ask you to perform any analysis techniques, Monday's quiz. I'm simply going to ask you to draw circuit diagrams. Okay, I'll give you a circuit or two, and I'll ask you to draw the circuit that is required to determine the Thevenin and Norton circuits. Okay, so in that case, this is the example circuit. If I want to find the Thevenin circuit or the Norton circuit as seen by R6, I remove R6. Now there are two terminals that are left open. I mark them as A and B. And then I analyze the rest of the circuit. Okay, I analyze the rest of the circuit. If I ask you to find the determine the Thevenin and Norton circuit as seen by voltage source V1, what would you do? You remove V1 and then mark those two terminals. Now V1 is gone, so it leaves behind two open terminals. You mark those, A and B, X and Y, Batman and Robin, doesn't really matter what you name it. But those are your terminals of analysis. In that case, we do not remove R6. Does that make sense? Right? You have a circuit, you can take any component in the circuit and you can say, determine the Thevenin and Norton circuit as seen by that component. Then you simply remove that component from your analysis. You got those 2 points. Now that is the circuit you need to analyze. And that is what I will ask you to do. Not any analysis, not any questions, just draw the circuit diagram. Okay. This is just to get you prepared for what's coming. So let's see, seven dependent sources. So that was them. Yes. No. Yeah, sorry to cut you off. So the question being asked is, do we reduce the entire circuit? Meaning all of the components that you see, R1, R2, R3, the answer is no. Did I get that correct? Yeah. So we are not, you won't perform any analysis. You're not doing any reduction, nothing. You're simply setting up the circuit to perform the analysis. That's all. You're drawing circuit diagrams. Okay. That's all you will do. So on Monday's quiz, that's all you will be doing. So only setting up circuit diagrams. Now, Norton was an engineer, Edward Norton, not the actor, but as an engineer working at Bell Labs in the 1920s. And he was, when you're working for audio applications, you were working with a lot of current sources. And so he postulated his own theorem based off of Thevenin's theorem, saying that you could also represent, instead of a voltage source, you could also represent the entire circuit as a single current source in parallel with the resistor. And so that's how Norton circuit came about. And so you could do the exact same thing, perform the exact same analysis. Instead of finding the voltage, you're now finding the current. But to determine the current, what you'd have to do is, again, if it's R6, I remove R6 from my analysis. And now I have A and B. Current needs a pathway to flow through. And so you place a short between A and B. Okay. So if you're doing Thevenin and Norton, you would say R6 is removed. I'm going to choose A as plus and B as minus. Doesn't really matter what you choose. And I would say this is my Thevenin analysis, and the rest of the circuit would be here. Right? This is for Thevenin. For Norton, and I'll draw it right here, you would go through, you have the rest of the circuit here. You have A and B. If you chose plus at the top, meaning at A, then your current should be flowing from top to bottom, A to B, high to low. So short between A and B and a current going through there. And the current, that current that you find, that would be your Norton current. Okay. So it's already 12. So if you need to leave, you'll leave. And I'll just continue for a few more minutes. Okay. But is everybody clear on what you need to do on Monday? Again, if you have any questions, definitely send me an email over the weekend, get in touch with me. I'll also be in my office today, definitely until 4, if not 5. So that's Thevenin and Norton equivalent circuits, meaning you remove that example. Yes. Yes. So the question being asked is, how do we find RTH? So RTH is the same. Okay, there's no such thing as Norton resistance. It's simply referred to as Thevenin resistance. And Thevenin resistance is simply Req for any network. So we reduce all the independent sources to 0. So if you have an independent voltage source, you reduce it to 0, which is what a lot of professors like to say, kill a source. So I just use reduce it to 0. Reducing it to 0 means you replace a voltage source with a short circuit and you replace a current source with an open circuit. So current source you simply remove, and a voltage source you replace with a short circuit. So all you're left with are a bunch of resistors in the circuit. And you find Req between A and B, and that's it. Yes.
The current was open?
Current sources are open, yes. So let me note it down here. So for RTH, replace voltage sources with a short circuit and current sources with an open circuit. Yes. To find RTH, yes. Yeah, good questions. The question being asked is, would I ask you to show the circuit diagram for RTH? And the answer is yes. I will ask you to do that. And sometimes you cannot manually find Req. Sometimes the circuit configuration is such that it's impossible. So then you simply use Ohm's law, because the relation between these three quantities is VTH is equal to IN times RTH. So if you have any two quantities, you can find the third. So you can find RTH by VTH divided by IN. But if you make an error somewhere in your calculations and you have an incorrect value of V or I, then your R is also incorrect. So as a working professional engineer, you never want to do that. Okay. And then lastly, the same thing as a dependent source. You have all studied analysis for dependent sources. You cannot zero out a dependent source. The theory does not work that way. You cannot reduce dependent sources to 0. That's the only thing to keep in mind. So when you analyze, you simply take it as part of your analysis. If it says beta IB or alpha times something or X times some value, then you cannot reduce it to 0. But dependent source stays in the circuit. Okay, you simply analyze it as it is. And you simply write one more equation to solve for that. Okay. All right, sorry to go over time. It's 12:05. Everything is being recorded and it'll be posted online shortly after I'm done with my classes. Yes.
Question is about the
So I'll give you a circuit diagram. So the question being asked is, what can we expect on the quiz? So I'll give you a circuit diagram and I will say, draw the circuit that is required to determine Thevenin, Norton, like Thevenin voltage, Norton current, and Thevenin resistance as seen by a particular component. Redraw the circuit diagram. That's it. Okay. No analysis required. No reduction, no analysis, nothing of that sort. Just set up the circuit to analyze. That's a good point that it should go away, but no, it doesn't work that way. Because it's not necessary that the dependence is on a source. The dependence could be on something else. We still don't reduce it to zero. No, we can't reduce it to zero.
question, Professor.